In a world racing towards smarter, cleaner, and more connected cities, one resource rises above them all: the power of the sun. From rooftops and highways to entire urban landscapes, solar energy is transforming the way modern society generates electricity and manages its growing demand. But how far have we come? What technologies drive this renewable revolution? And what future awaits smart cities built on sustainable power? In this documentary, we explore electricity generation from solar energy, its evolving technologies, real-world applications, and the innovations shaping tomorrow's urban life. Join us as we uncover how solar power is not just lighting up homes, but powering the future of smart cities.
Smart cities today are growing fast. With this growth comes a major challenge. Can our current power distribution systems handle increasing amounts of solar energy? Most of our power grids were designed decades ago. They were built for one direction power flow, from power plants to consumers, but with solar panels, electric vehicles, and digital systems, power now flows both ways. This causes problems like voltage instability, reverse power flow, overheating equipment, and inconsistent power quality. Our research explores if traditional power systems can keep up with the demands of modern, solar powered smart cities.
To understand this issue in depth, we examined several scholarly sources, each offering important insights for our research. First is the study of SHITE. This study provides a detailed overview of solar energy generation technologies, including how solar panels works, their efficiency, and the challenges in converting solar radiation into usable electricity. Their work help us understand the technical foundation of solar power and why integrating it into smart grids requires specialized equipment. Second is the study of Sinch and Gauche. Their research focuses on voltage regulation problems in modern electrical networks. They explain how unpredictable solar output can cause voltage fluctuations and power quality issues. This source highlighted the technical weaknesses of traditional grids when exposed to large amounts of solar energy. Third is the study of Kumar. Kumar and colleagues examined the impacts of distributed solar generation on distribution networks. They described issues like reverse power flow, transformer overload, and grid instability. Their findings help us understand why older systems struggles when many households and buildings start producing their own solar electricity. Fourth study is Tan and El Chacha. This study explores IoT-enabled fault detection in power systems. They show that using sensors and real-time monitoring can improve fault detection speed by up to 45%. This source demonstrated how smart monitoring systems can make solar dominated grids safer and more reliable. Last is RANA. Their research focuses on AI based predictive analytics for smart distribution systems. They explain how machine learning can predict equipment failures, forecast solar output, and optimize power flow. This source showed us the future direction of power system innovation using data-driven tools to support solar integration. Together, these sources help us evaluate the strengths and weaknesses of current power systems and the emerging technologies that aim to support solar-driven smart cities.
Despite these studies, we found several gaps that still need attention. First, many technologies like smart inverters or superconducting cables look promising but lack large scale real world testing. Second, solar energy is unpredictable. It depends on weather, time of day, and environmental conditions. Third, there are no standardized national guidelines for integrating large amounts of solar energy into all grids. Finally, IoT systems bring cybersecurity risk, and AI models require massive, high quality data that many countries, including the Philippines, still lack. These gaps show why solar integration remains a big engineering challenge.
Our thesis argues that to build reliable and sustainable smart cities, we must upgrade power grids using advanced technologies such as smart solar inverters, IoT monitoring, and AI based analysis to effectively integrate large amounts of solar energy. Traditional power systems alone cannot support the complex demands of modern urban environments.
First, old power grids are struggling because they were not designed for fluctuating solar output or bidirectional power flow. Second, new technologies exist: HTS cables, smart breakers, and advanced inverters, yet many are expensive and still not widely tested. Third, digital systems like IoT and AI offer better monitoring, faster problem detection, and improved forecasting, but face issues like cybersecurity and data quality. Fourth, traditional equipment alone is no longer enough for the increasing energy demands of smart cities. All of these points show that modernization is necessary for safe and efficient solar power integration.
Based on our findings, we recommend first is to upgrade aging infrastructure to support high solar penetration. Second is to use smart technologies such as IoT sensors, advanced inverters, and fast acne protection devices. Third is to develop national standards for solar integration, cybersecurity, and grade monitoring. Fourth is to support long-term testing programs tailored to local conditions, especially in the Philippines, where solar potential is strong. Fifth is to encourage collaboration among engineers, governments, and universities to innovate and test new solutions. These steps will help build efficient, safe, and resilient smart cities powered by solar energy.
Solar power is key for future cities. By working together and using smart technology, we can make our cities cleaner, safer, and more reliable. It's a challenge, but it's one we can solve.